Okay. Then.
Yeah. So.
Okay, you're ready to start.
Okay. So welcome to the Thursday session of the first session of Thursday for crypto, which is going to be about cryptanalysis. So we're going to have 4 talks. First, about symmetric cryptanalysis, and then there will be a small break, and then 3 more talks about more general types of cryptanalysis. Just as a reminder, everybody is welcome to ask questions in the chat that you can access from the very nice website. And all the questions will be relayed to the speakers at the end of the presentations, so at the end of the first 4 presentations, that is. And let's just start right away. So, by the way, if you have trouble asking in chat, in the Zoom chat, you may also ask in the Zoom chat, I guess. And you have the link actually in the Zoom chat. So anyway, let's start right away. So the first talk is going to be about differential linear cryptanalysis from an algebraic perspective by Mei-Cheng Liu, Xiaochuan Lu, and Tongtai Lin. And Mei-Cheng Liu will give the talk. Mei-Cheng Liu. Mei-Cheng Liu, do you hear me? We can't hear you if you're speaking.
We can't hear you.
Yeah. It's weird because I see his microphone moving in the Zoom, but I can't hear anything. I guess if there is a problem, we could start with a second talk, if that's okay, until this problem is resolved.
I would recommend Mei-Cheng Liu, you disconnect from Zoom and reconnect. Try again. And then go on to the next talk.
Oh, you mean meanwhile go to the next talk?
Yes.
Okay.
Until they figure it out.
So is that okay? I guess the next talk would be given by Xiaoliang Hua. So is that okay?
Oh, okay. Can you hear me?
Yeah. Would you be okay with starting? With
okay. Oh. Hey. I cannot share my PDF.
You don't have permission?
Oh.
Or? Okay. Well, you might need to give permission and then restart. So Mei-Cheng, have you reconnected? Okay, because otherwise we might just move to the third talk. Because we have a kind of a tight schedule, so we need to move ahead. The third talk would be given by Yaoping Chen.
Okay.
Oh.
Can you hear me?
Yeah.
Can you see my screen?
Yes.
Okay, I think I can.
You just need to make it full screen.
Okay.
So we're starting with a third talk then, which is going to be given by Yaoping Chen. And it is in collaboration with Lei Wang, Tao Wu Gu, and Tian Weng. And it is about revisiting the security of dbhts max beyond birthday bound in the multi-user setting. And yeah, it's up to you, Yaoping Chen.
Okay, thank you for the introduction. I'm Yaoping. Today our talk is revisiting the security of dbht max beyond birthday bound in the multi-user setting. And this is the joint work with Lei Wang, Tao Wu Gu, and Tian Weng. dbht mark are a class of marks that aim for achieving the beyond birthday bound security, including some ECBC, PMA plus, 3KF9, and the Latma plus. And interestingly, all of these marks following a similar paradigm that's called double block hashing sum. This paradigm is firstly abstracted out by Data et al. In FSC 2019. In this paradigm, a message will first map to a 2MB string by a double block hash function, and then to equality value of each half will be XOR sum to produce the final task. Let's recall the recent result regarding the dbht mark. Data prove that this generic framework can achieve the beyond birthday bound security with a bound that is q to the power 3 over 2 to the 2n. And then Lauren et al. Get further attack on this mark with a complexity that is 2 to the power 3 and 4. And very recently, Kim et al. Give a tight security bound for the dbht mark that is q to the power 4 thirds over 2 to the power n. At this stage, it seems the story of dbht mark is reasonably complete. But however, above beyond birthday bound result only consider single users. In practice, the adversary can typically attack multiple users at the same time and adversarially distributing its resources. This is particularly true for the mark. As one of the most commonly used cryptographic primitive in practice, marks are usually deployed in context with a great number of users. For example, marks are co-element of real-world security protocols such as SSL, SSH, IPsec, and has billions of daily active users in major websites. So one natural question is that how the number of users will affect the security bound of the marks, or more specifically, can the dbht marks still achieve beyond birthday bound security in the multi-user setting? If we use the step-up general reduction from single user security to the multi-user security for marks, that is, we just multiply by the single user bound by the number of users, then we will obtain the multi-user security bound of dbht mark. That's something like uq to the power 3 over 2 to the 2n, or uq power 4 thirds over 2 to the power n. Here u is the number of users, q is the number of queries. And if the adversary only issue one query per user, then the bound will be something like this, which is still the birthday bound or even worse than the birthday bound. So the direct analysis of mean security of dbht mark is much desired instead of rely on the loose generic reduction. So our contributions are manifold. We directly analyze the dbht mark in the multi-user setting, and we propose a generic multi-user proof framework for dbht marks. Our framework has two probabilities. The first one is that it is easy to use. One only needs to prove the hash path is on1 regular and on2 almost universal. The second one is that it can achieve a high security bound, that is beyond birthday bound security. We also demonstrate our framework with application to key reduce value of dbht marks and prove that 2K sum ECBC, 2K PMA plus, 2K Latma plus are all secure in the beyond birthday bound in the multiple setting. And for the 2KF9, the remaining one of key reduced variant of dbht marks, we cannot prove its security. Instead, we find a critical flaw on it. Note that this construction is proved to achieve the beyond birthday bound in previous work. and we find that one query is enough to break its security. We also show a birthday attack on several variants of 2KF9 and thus evaded that their beyond-based bound results. Here is our conclusion. We propose in our paper, we propose a beyond-based bound secure multi-user proof framework for dbht mask and prove that the 2K sum-ECPC, 2K PMA plus, 2K Lightmap plus are still beyond-based bound secure in the multi-user setting. And for 2K F9, we show it is insecure and also propose birthday bound attack on several variants of 2K F9. We also conjecture some interesting problems for future works. The first one is that whether can we fix the 2K F9 to go beyond the birthday bound again? This problem seems non-trivial since a single trick does not work as illustrated in our paper. The second one is that whether can we improve the current multi-user security bound of dbh mask to the 3N over 4BS security, just as in the case of in a single user setting. Okay, that's all. Thank you.
Thank you, Yaobin Chen. So, Mei-Cheng Liu, are you able to present your work? Okay, we can hear you now. Yeah, okay, we can
share my screen now.
Okay, I will stop sharing.
Okay, so the next talk will be what was originally planned to be the first talk of the session, if you're looking at the program. So it is about differential linear cryptanalysis from an algebraic perspective. And it is co-authored by Mei-Cheng Liu, Qiaoyuan Lu, and Dongtai Lin. And Mei-Cheng Liu will give the talk.
Okay, thank you for the introduction. Is there something wrong with my network? So I didn't share my face, so I just use the microphone. This journal is which I draw under Nidunda. Differential linear cryptanalysis and linear cryptanalysis are two most important tools in symmetrical cryptanalysis. And in 1994, Lanford and Herman proposed the differential linear and cryptanalysis. It's an ingenious combination of differential and linear cryptanalysis. However, there are few methods for estimation the best of the DL operation in the middle. A natural method is the experiment method, and the typical method is the manual attribution. And the linear method proposed at Eurocraft 2019 is DLCT. It is the more accurate than before for many suffers, including DS, separate, and SCON. Although there are still gaps, in this talk we study differential linear cryptanalysis from a different algebraic perspective. This is back the fact that the best is determined by the ANF, that is the algebraic number form, but it is infeasible to compute the NF of a cipher, or to simplify the computation to make it feasible. We simplify the NF to ATF, that is the algebraic transitional form. For the difference of the output of cipher, we use the differential algebraic transitional form. With the help of the DATF, we can estimate the DL best, and then we can try to find the good expression by resulting search. And then our final goal is to model key recover. To this end, we impose some conditional on the internal bit of the cipher to make an uncertain difference determine the first ones, and then search the good explanations. This process is the organic combination of the distinguisher search and the key guessing. This is the main idea of our technique. So what are the ATF and the DATF? We introduced the simplified transitional ruler for ATF, as shown in this slide. For the Boolean function omega without the binary variable x. If it involves 2 or more variables, then we define the ATF of omega as a new variable. Otherwise, we keep it unchanged. This rule ensures that the ATF of fx related to x is the ATF of f in very simplified way that can keep s unchanged. To compute the DATF, we can see the condition is shown in this picture. The big X is a vector variable, and the small x is a binary variable. The delta is the input difference. For the first one, we compute the NF, and then we apply the ATF to the results, and then compute the ATF of the second one, and then we repeat the steps again and again until observe the DATF. Then this is the DATF. Use the DATF, we can compute the best. We applied the technique to select different different tables surface, including also KKD, encryption, block cipher, zoom cipher, and the result for the estimation the best are shown in the table. Compared with the DFCT, our DATF is more accurate and can apply with more runs. And our technique can also apply to differential attacks. Compared with exact method, our technique is more powerful and more general. And our results for the killer attack are shown in this table. Especially our attack, we provide the first correct attack on the 12 runs on SPECT, and the first differential linear attack on the 11 run SPECT 112 and 28. To summary, we have shown the edge break perspective on the differential linear cross with the application to the CISA and the LWC finance ESCO, and the AS finance serpent, and the Eastern finance the Green V1. We believe that the tool is useful. Will be useful in both the criminalist and the designer of the symmetrical criminal system. Thank you for your invitation. That's all.
Thank you. So I guess we move to the next talk, which is about mini-nominal attacks revisited with key recovery, collision, and pre-match attacks. The talk will be presented by Xiaoliang Hua in collaboration with Xiaoyang Tong, Siwei Sun, Cheng Li, Xiaoyang Wang, and Lei Hu.
Oh, yeah. Can you see my screen?
Yes.
Oh, okay. Thank you. Thank you for introduction. I'm Xiaoliang Hua. I'm sorry to be here, and I will share our paper. Meeting the middle attacks revisited, key recovery, collision, and pre-major attacks. Firstly, I will introduce the meeting the middle pre-major attacks. Like the figure shows, the compression function is divided into 2 parts. The one is a forward check, which can be computed forward without knowing MB. And the other is backward check, which can be computed backward without knowing MA. And then we can mount the MITM attack. Several techniques are proposed to improve the attack, such as splice and cut, initial structure, and partial match. At Eurocrypto 2021, the MITM pre-image attacks were thoroughly modeled as constraint optimization problems by Bob et al. Like the figure shows, the forward check is from the starting state, SNC and SKSA lead to E plus, and the backward check is from SNC and SKSA lead to E minus. And partial match is between the E plus and the E minus. In their model, neutral words of forward and backward check are denoted by blue and red cell. No constants are denoted by green cell, and the unknown words are denoted by white cell. The objective function is to maximize the minimum field of the remaining degree of freedom and the degree of match. And the degree of DOF can be computed by initial DOF minus the consumed DOF, where the initial DOF is the number of blue and red cells in the starting state, denoted by lambda plus and lambda minus. Accumulated DOF consumed in backward and forward computation are denoted by sigma plus and sigma minus. And then I will introduce our automatical MITM key recovery attacks. Because our aim is to recover the key, we need to distinguish the initial DOF and the consumed DOF are from SNC or SKC. So we divided the lambda plus and sigma plus to two parts. In our attack, the full key space must be tested. So the initial DOF from SNC should be used up, while the initial DOF from the SKC cannot be depleted. And then we apply our automatical model on scanning. The structure of scanning is chosen here. In each round, the state is updated with subcells and constants and round tweaky, shift rows, and mix columns. Build the model and solve it. We finally identify a 23-round MITM key recovery attack on scanning N3N. Besides, we also analyze fork scanning. A summary of scanning and fork scanning is used in the table. Our attack is the first 23-round single key on scanning N3N. Finally, I will introduce MITM-based correlation attacks. The definition of T-bit partial target pre-image attack is given IV and T-bit partial target of D, find M prime such that T-bit of D prime is the same as the T-bit of D at the same position, and the other part of D prime is randomly obtained. So if we have an oracle A that can find a T-bit partial target prime with a complexity of 2 to S, then we can construct a correlation attack with a complexity of 2 to S times 2 to n minus t of 2 by calling A as follows. First, set T-bit randomly date as D prime, and then call A with IV and D prime in 2 to n minus t of 2 times. After the procedure, we have 2 to n minus t over 2 of n minus t bit random date, and thus there exists a colliding date with a high probability. According to this, we give an algorithm of a correlation attack based on MITM. And use our algorithm, we found a correlation attack on 6-round Whipple and 6-round Bristol 256 output transformation. Besides, we also found a correlation attack on 8-round Bristol 512 output transformation. And a summary of our results is shown in the table. And that's all. Thank you.
Thank you very much. And we move on to the last talk of the session before the mini break, which will be given by Daniel Keisters. It is in collaboration with Nicolas Bord, Johan Dijmen, and Gilles Van Asch. And it is about thinking outside the superbox. I will let Daniel explain what that is.
Hello, everyone. Thank you for the introduction. And welcome to this talk about the paper Thinking Outside the Superbox. So my name is Daniel Keisters, and as said, this is joint work with Nicolas Bord, Johan Dijmen, and Gilles Van Asch. So actually, this talk will be about the interplay between design and cryptanalysis. And the central notion in our paper is that of alignment. To give a bit of an intuitive feeling about what this means, consider the Rijndael block cipher operating on blocks of 16 bytes. And Rijndael with this block length is also known as AES. It consists of 4 steps, namely sub-bytes. shift rows, mix columns, and add round key. And what all of these steps have in common is that they actually operate on the level of bytes, so they process bytes. In this figure, you do not see the add round key step because we have actually transformed Rijndael into a cryptographic permutation by setting the key to 0. Now, sub bytes and shift rows commute, so let's swap them in this figure, and then you end up with this figure. Here in the middle, we see the composition of shift rows, mixed columns, and shift rows. And we can combine these 3 steps in a single large mixing block and call it M1. And this leads to the following recursive structure. And here in the top left, you see a box consisting of the parallel application of 4 S boxes, followed by a mixing layer M2 and the parallel application of 4 S boxes again. And this box is called a superbox, and it can actually be thought of as a bigger S box. And if you take that point of view, then this structure can actually be seen as, again, the parallel application of 4 S boxes, which are bigger now, and a big mixing layer M1, and then a parallel application of 4 S boxes again. Now, this superbox structure, combined with a mixing layer that uses MDS matrices, leads to easy proofs on the bounds on the trail weights, or differential and linear trail weight bounds. And these bounds are important in the context of arguably the most powerful attacks on symmetric crypto primitives, namely differential linear cryptanalysis. So intuitively, if a cipher has a superbox structure, then we call it aligned. Now, the way that we define it, alignment is a binary property. So either a cipher is aligned or it is not, in which case we call it unaligned. And in an unaligned approach, you, as a designer, avoid any grouping of bits when you design the round functions. So in many cases, that means that there is not a convenient combinatorial structure in there that makes it easy for you to prove bounds on the trails. So instead, you need to resort to computer programs, which in many cases are running in exponential time. So you can only get so far. So superficially, it seems like aligned ciphers are better in many aspects than unaligned ones. However, one might ask then the question why not every cipher is designed according to an aligned approach. So the general contribution of our paper is really that we have pointed out a number of side effects that show up when you are looking at an aligned cipher. And these side effects are potentially unwanted. And we've tried to quantify them. So concretely, we've looked at 4 ciphers, so Rijndael, Saturnin, Spongent, and Zulu. And they differ in their alignment properties, how strong their mixing layers are, different S boxes, the size of their S boxes. And note that the version of Rijndael that we have considered is actually the largest one. So that's the version on 256 bits, to make it easier to compare to the others. It actually took quite a lot of time to compute the metrics that we were interested in for this sample size. So in order to advance the study of alignment, we actually ask you to increase the sample size. And to facilitate this, we have made our software available at the URL that you see here on the screen. Onto the main contributions. So we have studied the differential and linear propagation properties of S-box-based round functions. So we've looked at the linear layer in isolation, measuring its say, absolute diffusion power. But we've also looked at the linear layer with respect to a partition of the space of bits defined by the S-box layer. And in this context, we introduce the notion of huddling, which is the decay that you see when you move from the bit weight to the box weight, where a bit weight is a metric that counts the number of active bits, so the number of zeros in the state, and the box weight counts the number of active S boxes. So S boxes which have a non-zero input difference or input mask. And we've also introduced the cluster equivalence, which is related to the propagation of so-called activity patterns through the linear layer. And these turn out to be important in the context of truncated differential cryptanalysis. Moreover, we have tried to give a formal definition of what we mean by alignment. we've computed exact histograms of the ciphers that we have considered. And a histogram, what we mean by a histogram is basically the distribution of the number of states, trails, differentials, linear approximations over their weights. So we have different histograms. And we've computed these for 2-round structures. And then based on the results, there were 2 ciphers that performed the best with respect to the metrics that we have looked at. And these were Saturnin and Zulu. So we actually repeated the same exercise for these 2 ciphers. And finally, we have done a qualitative study of the differential propagation aspects in Zulu. So we've looked at clustering of trails and 3-round differentials and found that actually there is no or little clustering in Zulu in this case. And we've looked at the independence of round differentials in 3-round trails, where by independence, I mean that the differential probability of a trail is actually exactly equal to the product of the differential probabilities of its round functions. And we found that for at least a 3-round structure that we considered, all the round differentials were independent. And with that, I would like to conclude and thank you for your attention.
Thank you. So we can move to the Q&A session. As a reminder, everybody is welcome to ask questions in the chat. There is a link in the Zoom chat, or you can find it on the conference portal. So far, unless I missed it, I didn't see a question, but I have a couple of questions of my own for the speakers. So starting with the first article for Mei-Chen Liu. I was wondering, so you adapt your attack to many different ciphers. How difficult is it to adapt the attack, or how generic is it? How much did you need to fine-tune to adapt the attack to all these different ciphers?
I'm sorry?
So you demonstrated your technique on many different ciphers, on many different targets, I mean. You applied it, you had many applications?
Yes.
How much work was it to adapt the general ID to each of the targets?
Do you mean the difficulty between different types for cipher?
Different types of targets, yes.
Okay, thank you. Thank you for your question. And I think it depends on the structure of the cipher. And for the stream cipher, ring 1, it will based on the NFSI, and I think using the differential, conditional differential attack is a good choice. But the differential linear attack may be not as good as differential attack. And for some other stream cipher, the division linear attack works well. And for the block cipher, such as serpent, as far as I know, the best attack on this cipher is the division linear attack. And for the authenticated cipher is same difficulty to get the best result. And but for some in some case with limited data or time complexity, it may be works well. To include, I think it depends on the structure of the cipher, but not the types of the cipher. This is my I don't know whether I answered well, but I think your question this is a good question, and it is
you answered.
Further. I need further study. Thank you.
No, because I was wondering, for example, it seems that your technique gives pretty accurate results in all cases on all the applications that you give. Your estimation by your tool is quite close to the experimental results. So I was wondering if you expect that would be always the case, or there are maybe some targets that are will be better than others. But I guess you answered that already. That
I
was the
think
meaning
it's
of my
close to
question.
the. I think the estimate value is close to the experiment value, but there are still some gaps. It depends on the case. I think it's difficult to give exactly estimate for the real value. And this three different servers performs different. So it's I think it's very difficult to answer a question in general case. I think the question is very good and need further research.
Okay.
Thank you.
Yeah, thank you. So let me check. Okay. Yeah. Okay, since there's a question in the chat, I will relay that one. So that question is for Daniel. Maybe you've seen it in the chat. So the question is, the strongest known examples of clustering occur when all S boxes are active. How does your approach handle this?
I would have to counter with another question, namely, what do you mean by handle this? I mean,
Timothy is welcome to join the discussion if you want to clarify the question.
Can you hear me?
Yes.
Yes.
Okay, good. No, so I mean, well, it seems like if you think about some things like invariants, where, for example, you have a linear invariant, you might have, so all the S boxes might be active. So it seems if you count only the weight, then, yeah, I mean, in this case, the weight is already maximal or very close to maximal, right? So that's what I mean by how do you handle this? Like, it's a bit fake, I guess, but.
I have to admit that I indeed find it a bit difficult to answer the question. I have to admit that many of these, say, the tables that we present and the histograms, although they are quantitative, in some sense, they're also a bit qualitative because they kind of give a hint of how things behave. So it's difficult to draw very strong conclusions. But I don't know if maybe one of say my co-authors has a better answer to your question, and if they would like to chime in.
If you want, I can step in. This is Johan. So if you have many active S boxes, then you get a lot of clustering indeed, and that's independent of actually the alignment or not. That's what we call saturation.
Yes, yeah, that's what I mean, kind of, yeah.
Of course. The point is actually in differential linear cryptanalysis, those cases are not interesting in these particular attacks. So we really concentrate on the resistance against differential linear attacks. And if you have a lot of S boxes active, then you got a very, the contribution of around has a high, very low DP or very low LP.
Why do you say these cases aren't interesting in the case of linear and differential cryptanalysis?
Yeah, because I think so.
But we have examples where this happens, right? So is it because it would only work for a few number of keys, or?
How do you mean we have examples where this works? So I mean, an attack.
Well, I mean, just one example. Maybe so in Midori 64, you know what this, of course.
Sorry, what?
We have this kind of an example. In Midori 64, we have this kind of an example, right? All S boxes active, linear approximation. Yeah.
Yeah, but I consider sound designs.
Yeah,
so
of course.
You have a sound design
but...
from the start. So if you have all kinds of weaknesses built into the cipher from the start, then yeah, you cannot do anything.
So, but I guess my question there is, how does that sort of relate to the alignment, then, or is that the case that this idea of alignment doesn't consider?
No, the alignment doesn't look at that. Alignment, we study it in the context of clustering of trails mostly. And also this independence of round differentials, those aspects that we treat in the paper actually. Yeah, that's where of course, alignment probably has an impact on other things too, but that we didn't study. That was out of scope.
Awesome. We are running a little bit into the mini break, but since we started a bit late because of technical issues, I think it's okay to run a few minutes into the mini break. Let me check. So there's a question by André Schrotenauer about the paper Meet in the Middle attacks revisited. The question is, how much time did the solver take on average for your applications? Let's say on a single PC, will it take like seconds, hours, or days? Like what's the order of magnitude? So I guess that question would be for Tialiang Hua. Tialiang, do you hear the question? Okay. So if Tialiang is not available, maybe this question can be handled on the chat or offline. I mean, by email or something. And yeah, I would maybe just have one final question for Yaoping Shin. You identified a critical flow for 2KF9. Do you have any idea how difficult it would be to fix? Is it difficult to say? Or?
You mean any idea to fix the 2KF9?
Like how difficult do you expect that it might be difficult to fix, or that, or do you maybe not know? That's fair.
I'm not sure. I'm trying to fix it now, but I think maybe the common trick does not help here, or maybe we need to invent some new kinds of 2KF9. But I think the construction is elegant. Maybe I have no idea now, but I think maybe there's some small smart idea can help you to fix it.
I see. So the answer, I guess, is it's difficult. It's not obvious how to fix it. Okay, thank you.
Okay, thank you.
I guess we can, if there are no further questions, and unless Tialiang Hua is back, we can move to the mini break, and we will resume at I don't know what hour it is for you, but at minute